So, welcome back, everyone. We are going to be continuing today on a topic that occupied us during our last class, but expanding on it in some notable ways, especially because some people here weren't able to make it last time. I'm going to be sort of situating us again in this headspace, and we'll then expand some of the coverage on it. So we've been talking about an important conceptual topic and more at a practical level, an extraordinarily powerful, useful, insightful lens by which to interpret behavior. And it is a lens which speaks both to system science issues and to a data science perspective, and as such may be interested to some people here from both perspectives. The topics which we've been discussing lie at the heart of reasoning about the behavior and underlying drivers for observed dynamics of complex systems. And I particularly noted last time the centrality of the idea of coupled nonlinear dynamical systems. That's a mouthful, but my emphasis on coupling was actually quite central to the argument that I advanced. And to the core idea, one of the core ideas, which noted last time, that the behavior of complex systems often exhibits a great deal of orderliness, a great deal of regularity, beyond what would commonly be thought. So when we're dealing with systems out there in the world, we often examine data. And one of the reasons that the broad enterprise of data science is so effective, and one of the reasons that we can elicit so much insight by assessing behavior of complex systems is the fact that while they may have many evolving agents as their parts, there's enough coupling between those agents. There's enough other structure in the form of conservation laws, in the form of dimensional considerations, that the net behavior is actually much lower dimensional and involves a lot fewer degrees of freedom exercised in fact than one would expect. And the particular construct that I referred to last time was this notion of model state space. And this is quite independent of talking about, it's a concept that exists also about systems in the world, quite independently of talking about models. So I spoke about it in models last time, noting that we can observe the behavior for a model over time using a classic, in this case, classic plot of time versus number of people in S, number of people in I, number of people in TI, or characterize an agent-based modeling model at any point in time by virtue of some summary measures, like the number of people are susceptible, the number of people, the count, or infected, the number of people are temporarily immune. But I noted that often there are hidden regularities. There's hidden structure there that often means that the behavior of the system is far simpler in a way, far more limited in its degrees of freedom than one would think. And I use the example here on conservation properties, the fact that S plus I plus TI must sum up to a constant, to capture the fact that, in fact, what we think might require 3 numbers to summarize the state of this aggregate model, in fact, that the state of that model could be summarized with just 2 numbers. And of course, it does reflect the conservation. And that's just the point here, that when we have these structural properties, ones of conservation, ones of dimensional structure, ones associated with coupling between agents, the observed behavior, the fact that you might be excused for thinking, well, we could have any number of susceptibles, any number of infectives, any number of temporally immune people. While you could be forgiven for thinking that, the actual behavior is much simpler. And here it not only is in 2 dimensions, it actually evolves along a trajectory which has very defined structure associated with it. Now, I had noted that this lens of state space, where we plot out, as we did there, in a single plot, a plot whose coordinates are given by, say, each of the state variables for a model, and we have to have a model, that provides an alternative to a time series-centric view. We could imagine plotting the behavior of the same model out over time, where we have separate lines for the number of susceptibles, number of infectives, number of recovereds. But here we've plotted it out with a different lens, a different characterization. And this characterization is extraordinarily powerful. It's extraordinarily powerful when we're dealing with models, but also, and this is my point, or a big point of last time, when we're dealing with empirical data. And I noted that it's a particularly useful framework because often our systems, our underlying systems that we're studying, or the particular model that we're studying, if we have a model, can exhibit quite different behavior in different areas of the system. In certain areas of the system, it'll go to one outcome. In another area of the system, reflecting path dependence, reflecting potentially lock-in effects and others, it can go to a very different outcome. One where the infection dies off under certain ranges of, say, starting conditions, and one where it takes off and remains entrenched in the population, remains endemic. And in the sweep of our last lecture, I argued that while we're demonstrating these constructs here, as in terms of state spaces of aggregate models, they can be adapted to, these ideas can be adapted with equal or greater power to agent-based models. And I gave reference to the fact that often we use summary measures to parsimoniously place, depict the model's behavior in a summary state space where the state space exhibits coordinates, which are given by counts of people in different states, rather than dealing with all possible combinations. I had emphasized that last time that if we consider the actual dimensionality of a agent-based model with n agents, capital N here, and if each agent can be one of S possible states, I'm using S to denote the number of theoretical possible states rises as S to the n power. Because each person can be one of S states. Person 1 can be one of S. Person 2, one of S. That's S times S or S squared. Person 3 can be one of S. So S times S times S, S cubed, etc. Right? And this rapidly becomes, just extraordinarily large as a diagram, or as a number, the number of possible states. But if we consider summary measures, counts of individuals in different states, for example, we can often provide something that has the flavor of a state space, and in fact exhibits many aspects of a state space. So we saw a model last time, or we saw a depiction here of a model. And I argued that the model exhibited a lower dimensionality in behavior with individual trajectories evolving in ways that reflected regularities, that the system would orbit around a certain state here, a sort of stochastic steady state, in ways that were that exhibited noise, exhibited variability, but still had broad regularities of movement. And you can see that in these graphs above for lynx and for hares. Now, this was coming from a model. It was coming from this one. And if time allows, we'll dive into that this time. I also gave another example of an ABM that where infection spreads regularly and where we see low dimensional structure, sort of very ordered structure coming out of it that exhibits a great deal of strong regularities. Stochastic, but an orderly character that's pretty clear. For example, here, the number of people, a number of times that individuals within a high SES group or low SES group might have had some level of economic gain, for example. So low SES being distinguished from high SES by quite a gulf. And here, income versus personal infection state chart. Here we have the higher the income, the lower the level of infection. State spaces provide this alternative lens, which is very powerful for understanding evolution. And I'm going to come back to some of the uses of that. But then I ended up taking this in a different direction. Although I emphasized the way in which the nominal dimensionality of a space, here 3 down, differed from the intrinsic dimensionality 2, or the nominal dimensionality here, intractably large number of possible states compared to the, in fact, occupied dimensionality, occupied, in fact, by the ABM, which I argued evolved in a lower dimensional manifold, something whose actually dimensionality is vastly smaller because of the coupling between agents, because of conservation, because of dimensional considerations. I took this in a direction of noting that these analysis methods, well, I've motivated them with models, ABMs here, with aggregate models, apply just as much to empirical data. And I noted Taken's embedding theorem and the fundamental, which argues that any sufficiently broad system that exhibits, or nonlinear system that exhibits coupling, and therefore evolution of one variable, like the evolution of the number of hairs, is entangled with the evolution of the number of lynxes that prey on that hare, means that there's lower dimensional structure that lowers, that constrains the structure of this system. And it means that the information about any one variable encodes information about others that drive it. So the information about the hairs encodes information, and you can go back to the video from last time to understand, for those who weren't here, encodes information about the number of lynx that prey on the hairs. Hairs are X here, and the information on how they're changing and the number at any one time encodes information gives us information about the number of linkses there must be. And similarly, the information, if we only have information on linkses, it gives us information about hairs. And the important thing here is that, well, again, I'm motivating this based on some model structure, some ordinary differential equations in this case. This is true about systems in the world. It's true about systems where we don't have a model. It's true in a model-independent fashion. And it provides us a lens of understanding data from the world, quite independent of any model. And, I put up here some examples of plots that draw on these sort of methods with empirical data. Here, plotting out, for example, daily reported cases versus daily reported deaths for 7-day averages of each. And you can see a very regular sort of cyclical structure here that reflects successive waves of infection. This was from the UK government, the original data from the UK government during COVID, right? Same thing, or a similar principle here, daily admissions versus the number of beds in hospitals full. We can see interactions between these that lead to structure rather than having data all over the map where you could have any number of admissions together with any number of beds full. If you know something about the number of admissions, it tells you something about the number of beds. Either you're decreasing in your number of beds and number of admissions, or you're increasing in both, but they're highly coupled. Same thing here with total confirmed cases here on the x-axis and new confirmed cases on the y-axis. We see country after country here with very regular structure coming out of it. These are very complex populations involving many, many individuals, et cetera. But we see the same patterns emerging from these complex, large numbers of individuals. Here are new cases in the past week and change in the case rate, again, capturing regularities. Independent of models. These are not in any way dependent on our models. We are characterizing patterns in the data that whisper to us about the underlying system that's giving rise to them. But importantly, these are data about complex systems where the underlying emergent data from the system is lower dimensional. It has this lower dimensional character. It has a great deal of regularity to it, which comes, across many, many cities here within the UK, comes across many countries here, many particular hospitals here, et cetera. And it reflects the fact that we do have this ability from empirical data using the right lens, the lens of embedding, this association of vectors with each point in time, we can reconstruct this structure of an underlying state space that's driving the system. This is independent of model. This has nothing to do with having a model of it. These are model-independent approaches that let us peer into the underlying drivers behind this data. And importantly, they let us take a small, just data on one component of the system and give us understanding about what's going on in others of the system that are driving this one or that are affected by it. It tells us, it's as if the light in one area of the system that illuminates, say, the number of hairs here, reflects off what's going on elsewhere in the system so we can peer and see what's going on elsewhere in the system from the data on this one time series, on this one variable. And the way we did it, you may recall, reflects the fact that if we have a time series, call it Y, of values over time. So we have a value for day 1, 2, 3, 4, 5, etc. We can, for each of those days, except those at the very beginning, whose preceding ones are cut off by the beginning of the data, they're censored by the beginning of the time series, we can build vectors here. So for time 100, we would build a vector of the value of the time series for time 100. That would be the first element of the vector, the value of the time series at time 99, day 99. So that's 100 minus 1, let's say. The value of the time series at day 98, that's 100 minus 2 times 1. And I'll speak about the choice of this tau, and right now I'm referring to a tau being 1. But for each time, we get a vector. And here I've listed 3, but in general, we could have n plus 1 entries here, where we successively look earlier and earlier by multiples of tau. Okay, so for each point in time, we get a vector. And we place that vector in state space. So if we have a time series of cases, 1 case per day, we'll place for each time point, that's each of these dots, that will give a vector. A certain value for cases at time t will be the value along this axis here, value along this axis here, this axis here will be cases at time t minus tau. You can kind of see it labeled there. That must be this one here. Cases of t must be this one. In case of t minus 2 tau must be this one. So each of these points is situated with x, y, and z coordinates given by its cases now, its cases at t minus from tau ago and 2 tau ago before that. And you'll notice the structure here. This is from successive waves of infection. These loops, this is colored by when in the time series it occurs. So things that look yellow are appearing close together. And we go from there to orange and there to red, for example. Earlier were things that are sort of green and occur within a green context, and then morph into other countries, other colors, I believe, such as blue, etc. Now, often here, we take these vectors and we create them not for the original time series, but for what's called a first difference of the time series. So this reflects the fact that often this time series reflects an accumulation of some sort. Maybe it's the count of people who are infected. And what we're really interested in is knowing how is that count changing. That may be most directly affected by other variables, for example, that we don't observe. And we're interested in assessing it. So we take our time series here and we take the difference and then we do, so the difference between what's measured at time 1 versus at time 0 or time 2 minus time 1, etc. This is sort of our new time series. This has a number here, a number here, a number here. It's a long time series. And then we embed this. We go through this process like this of embedding it. And you must say, well, why the rigmarole? Why all this work? Well, because it provides this extra lens that's very powerful. It takes time series, which are otherwise looking perhaps inscrutable, perhaps unpredictable, perhaps random, perhaps, lacking order, lacking clear structure all over the map, where you have difficulty predicting what's going to happen next. Sounds like some time series involving outbreaks that I know. And you end up embedding it such that from any one of these, you can reconstruct the underlying state space of the system. You get something like this. Reconstruction from X alone, you get something that depicts the structure of the underlying state space. It depicts a picture of this underlying nonlinear system. What I've shown in this plot here, mind you, is if we had a God's eye view, a magical view where we knew what X is, Y is, and Z is, these are the other components of the underlying system. This is what it would look like. And what my point here on this image is that we can reconstruct something which is homeomorphic to that, which is basically just a squish version of that, where we don't rip it or tear it. We can twist it and stretch it, but we can't tear it. We get something that looks all the world like that from a single one of these alone. It provides us this lens as to the underlying state space of the system, even though we only have one variable. Just like the number of hairs and the dynamics of the hairs are telling us a lot if only we have the ears to listen to it. Or if only we have the eyes, we open our eyes to it. It's telling us about their drivers, the number of links, for example. Now, this can provide us with this extra window on complex underlying time series. Now, one thing I didn't have time to discuss last time was the way in which this delay embedding, you recall that we taking for each point in time, the value at that point in time, we're creating a vector. What vector is it? The first element of the vector is the value at that point in time. The second element of the vector is from that time series, tau ago. The third point in this vector is it from 2 tau ago. This tau, the choice of the tau actually makes a significant difference. This is an area one has to be quite careful about when doing time series embedding. So we may have a time series, and in fact, this is, I believe, one of these earlier ones that I was showing, where we have a small tau. And here, if you consider it, we have a very small tau compared to the speed at which the system evolves. Maybe we're looking at time series associated with new cases of diabetes, and we're looking at daily time series. Well, for a municipality, the number of people with time series now, with diabetes now, and at a given day, and a day ago, and 2 days ago, if your tau is 1, then the value you get for this point in the vector, for this point and this point, will be very similar. Okay, maybe they'll be off by 1 or maybe 2, but they'll be very, very similar. The value here will be almost the same as this, almost the same as this. The number of people with diabetes minus, maybe they're off by 1 or 2. In short, they'll be very close to the diagonal here. Right? If they were exactly equal, they'd be on a diagonal exactly. The number of people with, if you plotted out the number of people plotted out a vector, the number of people with diabetes now, the number of people with diabetes now, the number of people with diabetes now, you plotted that out for all different nows, all different days, you would get an exact line here, right? The value of the X, Y, and Z coordinates would be exactly equal if tau were 0, right? Would be tau were 0, it would be an exact line. The value now would tell you the first element, the vector, the second, the third, or the value at a given day would tell you first element and a third, they'd be equal. If tau is 1, they're going to be close. And as a result, you're going to get them clustered around this diagonal very tightly. As you broaden tau, if we double tau to 2, we'll see something that's a bit broader. It's not quite as clustered. Tau is 4, we double it again. Now we start to see some additional structure emerging, structure that was hidden here. Sort of these trajectories were collapsed in. But there's still a lot, packed into this. We go to tau equals 8. Okay, now we start getting some broader depiction of these successive waves of infection. And then going to some sort of endemic state. Tau equals 16, something similar with not too much difference here. So the choice of tau makes a difference. This would be another example from that Lorenz system, a classic nonlinear attractor system that's often used to describe chaotic systems. Invented by atmospheric physicist or discovered by atmospheric physicist Edward Lorenz at MIT in the I should know. I'm going to say 70s, maybe it was late 60s, but it could have been even earlier. So here, the effects of embedding on that system, if we embed successive data points of X alone, for example, with an embedding of 1, we get something like this. Embedding of 2, we get something like this. Embedding of 4, we start to see structures that are less directly insightful for the underlying system, for understanding that structure of the underlying system. It's capturing certain movements over broader time sort of delays associated with this, but it isn't as parsimonious in its depiction of the underlying system. So there's a certain amount of tuning here that's needed. Similarly, even the choice of this space here is important. We chose here three-dimensional space because it provides a convenient space in which to summarize this. 3 dimensions. Jeff, yes.
For the effects of tau and embedding, one that has the
this one?
Yes.
Yeah.
Is there any correlation between the value of tau and the number of points, the number of
lobes
figures that you see?
I would expect so. I mean, casual observation suggests, yes, that the number of lobes that you see is very much determined by the value of the delay embedding. Now, if you were to ask me what is depicted here an aspect of the structure of this system, I would be inclined to answer yes. There is some higher order structure that's probably not obvious here. Maybe we'll go back to our finer grained depiction of this. There's likely some non-obvious structure involving the fact that some of these trajectories here on the outer side may go to inner trajectories here, which may loop around to inner trajectories here, which make their way to outer, or something along those lines. Those are not evidence-based comments, but casual inspection would suggest that the coupling between these is far from random. Like there's a way in which this is flowing over that involves no cross paths, and where you have things that are on one side here flowing, and indeed it's like the outer ones here seem to go to the inner ones here, etc. And so I do believe there's some sort of higher order structure that this is picking up, like with larger time series, or larger tau. You're getting away from you're picking up sort of linkages between where things are flowing between these. Now, whether this is useful for your task, a given task is another matter. I want to talk about uses of these embeddings, And it may be in certain cases you do want to be sensitive to that. But if your goal is to kind of understand some basic elements of the structure of the underlying manifold over which this is evolving, that it has certain holes in it, that there's circulation between these lobes, etc., that may not be as well served by this as it is by this. That's a conjecture. I don't know that for a fact, but it would seem sensible to conjecture that. Okay, so let's talk about this embedded space. So like, all right, so you can go through this lens. We can take time series data from the world or from our models. We can look at it with this special lens, this special, microscope or multispectral imager, and we can see something different than we do with time series. With time series, we see certain behavior, and that behavior often clues us into important dynamics with the system. That's important. This gives us a picture of that behavior from a different perspective. It clues us into other aspects of it. I like to think of it as viewing the system from a different angle. Or instead of viewing it in visible light, viewing a system in the near infrared and far infrared part of the spectrum. You can pick up differences. You can pick up different aspects of its behavior than will be obvious. And sometimes, as is depicted here, the time series is not a terribly hopeful way of communicating the structure of the system. Looking at it like this hides a lot of the structure, or it does not manifest the structure. It's not making it manifest. It's not rendering it in a way that it's obvious. But meanwhile, a state space picture brings out that structure in a very strong way. Well, what of that? Are we just sort of using it for aesthetics and for the pleasure of seeing hidden order where there wasn't any? Well, no, there's a lot of values for this, and I want to talk about those. Yes, we can recognize hidden structure. We can recognize that these time series, far from being random, are in fact loaded with hidden structure. That's important. They're not just evolving willy-nilly. They're not evolving with no rhyme or reason. They're not evolving just dictated by stochastics. They may be, and a lot of people looking at this time series might think it is evolving in some sort of completely random way, but it's not. And knowing that is helpful for knowing about the prospects of modeling it, of characterizing it. So the fact that it has order, it has regularities, lends hope to our ability to model it effectively, to understand it better from a data science perspective. It allows us, importantly, on those lines, to computationally assess dimensionality. Had I additional time prior to this lecture, I would have created an additional slide after that, noting that when we reconstruct the state space of a system like this, or like this, or like this, etc., we can readily use a variety of tools to quantitatively assess the dimensionality. What do I mean by that? Well, I had argued that these complex systems often evolve in lower dimensional manifolds, that they're in a nominally high dimensional space. In this case, just, astonishingly high, with number of states that each agent can be in to the n power. It's astonishingly high. But what we see is a very low dimensional structure emerging from it. What's the significance of that here? Well, it suggests that the system has enough order, it might be able to be modeled parsimoniously in a more simple way, or that highlights the importance of capturing certain coupling in our models of the system using, say, agent-based model. So here we can run dimensionality assessment tools. This is something we've done on empirical data as well as model data using tools such as the Hausdorff dimension, the dimension, so it's called the box counting dimension. These are different ways of assessing dimensionality within systems. And I given you an example last time, which I won't try to recreate, but which showed that, I gave an intuitive argument for why if you count the number of points as you consider a broader and broader radius around a certain point, if the number of items, number of data points rises linearly with that radius as you go from a small radius to a larger and larger radius, if the number of points that you include goes up to the first power, the radius to the 1 power, that's an indication it's one-dimensional. If it goes up radius to the 2 power, you may have a kind of bent manifold, a manifold that's not linear, but here, as you have a larger and larger radius, the number of points included in that radius goes up with the square because it's going up with a circle around it intersected with this. A somewhat kinked circle potentially if the manifold is bent. And if we're dealing with a 3-dimensional surface, the number of points in it will go up with the cube. We can readily assess those things. There are, large numbers of libraries in choose your computational environment, R, MATLAB, Python, SciPy, that will allow you to measure these things and SciPy related environments. Importantly, and this is really notable, when it comes time to discussing calibration of agent-based models, which will soon be a notable focus. While we commonly think of calibrating model against time series, we have data over time and we try to adjust our parameters that are less well known so that the model characterizes the trends in or the rough values of those time points at various time points. We have a different lens here. We have a different way of summarizing the regularities in system behavior. We can take empirical data and create state space plots. And we can hold our model to account. We can ask it to try to match the state space depictions of empirical data. That's picking up different aspects of this situation than we're normally calibrating against. When we calibrate a model, we're seeking to have the model reproduce as best we can the patterns in the empirical data. These are patterns here just as important and arguably more important because they have to do with the underlying state space of the system than the patterns we see over time. The patterns we have to do with the underlying state space driving the system. They're guaranteed by Taken's embedding theorem to be closely related to that state space, to be a reflection of that state space. More than that, mark my words, more than that. Even if we plot out when we calibrate, if we have data from the world about one time series, and we try to get the model to match it, we're doing a good job of trying to match a time series from the world against a comparable time series from the model. We equip the model to output things comparable to what we see from the world. This is all an important step. But these state space plots, these here plots, are guaranteed by Taken's embedding theorem to contain information about multiple, not only the value being measured, but they whisper about the structure of the system giving rise to it, the other variables giving rise to it. These are guaranteed to encode information just as much as here we see information just like that we would get out of X versus Y. We get it out just from X. We can match our model to these sorts of structures, to these sorts of shapes, in order to ground it in the dynamics exhibited in the world that cuts across internal state variables of the system. So what I'm saying is, by taking model output and embedding it and calibrating that structure, trying to match that structure against comparable structure from the world, from embedding empirical data, we get out something that's an incredibly valuable tool to add to our ability to calibrate a model that can ground it more fully or in a very complementary, arguably, possibly synergistically way to what we do when we work with time series. So that's a very important tool we'll be returning to in our discussion of calibration. And it has to do with Taken's embedding theorem, this ability for either data from models or on the other hand, data from the world to use this lens to see hidden structure. And in this case, to match that hidden structure between the model with what we see from the world. Now, there's another important way in which we can use these data. We can use them for model-free prediction. So when we see these regularities here, they're not merely food for thought or curious aspects of structure. They're not merely reassuring encouragements of the prospects of modeling these systems. Speaking about the underlying order to them, that if we only build a good parsimonious model, we could elicit. No, there's something more than that, right? They provide us a way, using just data from the world, no data from models, just we may not have a model. Commonly, we won't have a model early on. But when we start accumulating this data, they provide us a way of projecting forward, of model-free prediction or forecasting from state space. Just as if we have a plot of a hurricane geographically, and we can project forward where it may go subsequently. So these sorts of data from the world provide a sort of model-free world, or model-free way of anticipating what is coming on, what is likely to be the case in coming days, or coming periods of time here. Oh, okay. Yeah. So these provide us this tool to sort of anticipate what may be coming next. You could see these are sort of bending around in common ways, and based on what we see from one, we can be encouraged to be able to project forward in a way that will probably give us a better sense of what is likely occurring than if we simply linearly projected forward a time series, because these sorts of plots build in information from often different time series, right? Deaths in cases here. They build in information from across time series that can inform our prediction more effectively. Okay. I will finally just mention an element that cuts to the heart of some of the value we seek to get out of dynamic modeling and cutting edge areas related to machine learning. I sit here as a systems data scientist, someone who's been using data science centrally in our work since the 90s, and who couples dynamic models with machine learning in a way that goes back, again, decades. So an important feature that dynamic models seek to bring to the table is positing causal structure of a system, positing a mechanistic understanding of what's driving what across many, many pathways, giving rise to emergent behavior, giving rise to systems effects, but ultimately positing impacts of causal mechanisms that are quite specifically posited to be causal. And the reason that's important is because we can use them, unlike classic machine learning, to reason about counterfactuals. With classic machine learning, including powerful techniques like deep learning, that are all the of central importance in advancing many contemporary areas of application of machine learning. Those techniques are contingent upon patterns from the past, associations from the past, continuing into the future. It's as if we have a very powerful vehicle that is set to go around in a racetrack which is a very regular structure, where we've been tells us a lot about where we're going. Looking at the rear view mirror, looking at the curvature will tell us what sort of curvature lies ahead. We're in the straight and narrow. We're in a regular situation where the past, the associations of the past will hold for the future. We can be very efficient about understanding, predicting missing data, classifying, undertaking what in machine learning are called the regressions or predictions of continuous variables, etc. And that's all very powerful. But if we go off-road, we change the data generating process. The associations on which those machine learning models have been trained, and that's what they're trained on, associations, correlations between different variables, very complex, very rich correlations, but correlations nonetheless. Those may be altered. If we have a vaccine rolled out where there wasn't one previously, it will alter the relationship between age and death rate, especially if older individuals tend to have higher rates of uptake of the vaccine. If we have a new therapy come out, it will alter things in ways that may change the association between clinical symptoms, the time of presentation, and risk of mortality. If we have a wholesale attempt to deal with adverse childhood experiences, over the course of 100 years. It may dramatically change the impacts of the association between lower socioeconomic status and other aspects of disadvantage and chronic disease outcomes and mental health outcomes later in life. If we intervene in a system, or if counterfactuals such as the arrival of a new variant arise, it will alter those associations. Dynamic models help us reason about these. And what these tools provide us a way of doing is assessing causal influence. They allow us, through what's called convergent cross-mapping, to use the underlying state space of the system as reconstructed via Taken's embedding theorem to reason about causal interactions between different variables. And what we're doing here is assessing the ways in which one variable ends up within a state space portrait, within the so-called shadow manifold, the reconstructed manifold, how information about the closeness of values within that manifold predict the closeness of values within another manifold, within the manifold for another variable. And here, by assessing the coupling between these two variables in reconstructed space, in the essentially the state space of the system, not in the just time series, in the state space, closeness in state space, we can end up recognizing ways in which one variable impact another in terms of their causal impact. We can recognize non-causal interactions that may be simply statistical correlations or associations, inverse or otherwise. We can look and find weak or indirect causality and distinguish it from strong causal impacts. So here, we're really talking about bringing together data science, and this allows us, I should say, to do causal discovery, to recognize variables that we're not sure if A causes B causes A causes B, and B causes A, reciprocal causality, or whether there's some Z that causes both, that drives both A and B, leads them to be correlated, but in ways that neither is driving the other causally. This provides a way of teasing those things out. In our experiments, as well as the work of Sugihara and others, including the pages of Science, these techniques have found to be very insightful for assessing causal impacts. They do have shortcomings that require a long time series, and they have tricky issues dealing with missing data, etc. But they are very powerful techniques. So, in closing, data science and system science in this area are synergistic, and really what we're talking about is bringing together both of them here, recognizing that state space for systems in the world where we may have no models, that structure of that can be elicited in these structured ways. And if we do have models, to ground those models, the assumptions of it, to calibrate those models, to cross-check those models in terms of causal influence, or in terms of how one variable is coupling with another, we can use state space reconstruction, this reconstructing of state space using these vectors, delay series and delay embedding, can give rich understanding. And, this broader enterprise of systems data science here can help us go beyond reasoning about single variables being measured over time, which is powerful, but use that to give understanding about other areas of the system, to illuminate other areas of the system on which we may not have any direct information. Gives us clues as to what's going on in ways that drive this. This can allow us to learn more deeply from when we do have data about the world, and can help ground our models in ways that can help us reason out counterfactuals. And can help us, when used fully, ground causal assumptions in our models by helping us assess the degree to which one state variable is causally driven by another, or the degree to which they may simply be correlated statistically or exhibit causation in the other directions or in both directions. So that's all we have time for today. We're going to be, with this discussion, we're going to be wrapping up some of this module. Although it is a component we may return to within this data science, combined data science, system science lens, we may return to on our tutorial, our lab on Thursday. So thanks for your attention, folks.